There are so many useful applications of Riemann sums, and we can use them to set up integrals that represent quantities other than areas and volumes. For instance, we can find the length. So if we want to find the length of the curve from P to Q, we could actually look at this curve and break it up into tiny little segments, so like the one that we've got here. So here, now I've magnified here. This is in fact a little triangle, and of course the length of the hypotenuse is given by Pythagoras' theorem, which is the width squared plus the height squared square root. Now, that being the width. Now, if we partition this interval into n subintervals, on each subinterval we can define a small quantity delta s that approximates the length of the piece of the curve. So we want the sum of I equals 1 to n of delta s, and then take the limit as n goes to infinity. So our arc length of PQ is in fact the limit of n goes to infinity of the sum of I is equal to 1 to n delta x subscript I. And of course we have an expression of delta x from the previous slide, which is n goes to infinity. I is equal to 1 to n of delta x all squared plus delta y all squared. Now if we divide through, so just looking at this section here, so look at that, if we divide through by, so I'm going to do this way, by delta x all squared delta y all squared over delta x all squared. Now if we're dividing through by this, we have to multiply it by that. But what this means is we can now take this out. So we have 1 plus delta y over delta x all squared times by delta x. And this is in fact in the form of a Riemann sum. So there's our function and then our delta x. So this is in fact the definite integral from a to b of 1 plus dy dx dx. Pretty cool, hey? So we can now use this to find the length of the curve of y is equal to x cubed. So if I draw it, looks something like this. Now I'm not the best at drawing curves. Okay, so that would be 5. That's 125. Okay, but we want to find the length of the curve from 0 to 5. So it's in fact this region here. Okay, so we have, well, we know from the previous slide, a to b of 1 plus dy dx all squared dx is equal to the arc length So we have 0 to 5, 1 plus, first, y dx is in fact 3x squared, 3x squared dx, 1 plus 9x to the 4 dx. Now, using Mathematica, we get 125.68. So I'm just going to write this down. Clearly, it's useful to have ways of evaluating difficult integrals. And one way is the trapezoidal rule, which we will be looking at later in this lecture series.